All right, so we're going to add another energy form to our list of energy equations. If I were just to push this block a distance s, it has mass m, and I want to know the velocity at the end of that distance, let's say that coefficient of friction here is 0, so it's like perfectly friction-free ice. We're going to put in work, and it will turn into kinetic energy. So force times distance will equal 1/2 mv squared. But it kind of looks like there's some friction there. So, by the way, if I solve this, I get velocity equals, because we want to know the velocity, 2f s over m square root. But it looks like, and yes, indeed, there's a little friction here, correct? So what should that do to the final velocity compared to when this was a friction-free surface? Slow it down. That's correct. So we need, in energy terms, something that works for the energy lost due to friction. And friction is typically bad. It is the bane of engineers everywhere, right? Energy lost due to heat. And so we will just very quickly derive an equation for work done by friction. Now, regular old work is force times distance. Work done by friction is going to be the force to overcome friction times distance. So work done by friction. Based on the equation that's on the board, the force to overcome friction is mu times the normal force times the distance. And yes, indeed, that's it. So it's really just our force to overcome friction equation with distance attached. Easy peasy, right? I'm Martai. What, you need a computer? Go. Okay. So now let's do this same problem, but we're going to throw work done by friction in. So initially we have positive work, the work that made the mass go fast. And we also have some work done by friction. Do we add or subtract that? Always, because friction is bad. And then we want to know how much kinetic energy is left over. So work is still force times distance. Work done by friction is mu times the normal force times the distance, and that'll equal 1/2 mv squared. Force times distance minus mu, and what's the normal force in this case? What's the normal force? M times 9.8, very good. So mg is the normal force, distance is s. And then if I solve that equation for velocity, I get velocity equals 2 times the quantity, Fs minus mu mg s. I suppose I could have factored out the s. All divided by mass square root. And if you compare it to this, it's a little smaller based on the square root of that expression. Okay? So now that's a lot of variables. If we put numbers in, this number will be bigger than this number. This velocity with no friction will be bigger than the velocity when we throw in friction. Pretty easy peasy, right? What happens if I tip it? What happens if we put the mass on a hill? You want variables or numbers? Variables. Wow, you guys are brave. Okay, let's say I have a mass and it slides down a hill.
Did we ever get to do like a hill with bumps and stuff?
Like a mogul hill?
No, okay. You know how sometimes if you roll down the hill, you kind of like sometimes it's not just like flat. It's like kind of like
Like changing angles?
yeah. So you have like little parabolas.
No, because
Like if you took physics.
maybe. Parabol, yeah, because you have to take the integral to take the area. Maybe. I don't know. I'll ask the supporting. Good question. So let's just say the mass slides down the hill. A distance s, and I want to know how fast is it going at the bottom of the hill. It starts from rest. Good question.
Gravity.
Good answer. Question was, what's the force? Answer is? Gravity. So, what is the good energy that makes it slide fast? Gravity. So, work done by gravity. What's the bad energy that slows it down? Work done by friction. So, I'll subtract that. At the bottom of the hill, what's the form that we care about? Right, kinetic, because we want to know how fast. Try filling that in. Try filling in the work done by gravity, the work done by friction, and kinetic energy, and let's see how you do. Perhaps there would be a triangle there.